Let us just wait for a few more minutes before starting the session. Somebody else is joining.
Okay, let us start today's session. Uh, so, uh, is the screen visible to you and am I audible?
Yes, sir.
Okay, so I welcome all of you to the ninth live session of the course Fundamentals of Manufacturing Processes being offered by Professor D.K. Dwivedi of IIT Roorkee. So, and as in for myself, I'm a Vidyabhay, PMRF PhD scholar in the Department of Mechanical Engineering at IIT Bangalore. And today I shall be discussing with the material removal process, the continuation of the material removal process. In the previous class, we have already discussed about the basics of machining. Today, we shall be discussing on the grinding process, the basics of the grinding process, and also some other phenomena related to the machining process and the problems related to these. So, yeah, let us begin. So, in the previous class, we were discussing about the different types of wear that occurs during the machining operation. So, related to the abrasive wear. So, why does the abrasive wear occur? So, abrasive wear occurs due to the cold bond of chip with the workpiece, the hard particles in the workpiece, oxide layer formation, or the softening at the softening at high temperature. So, which of these results in the abrasive wear? Can anybody tell me the answer? Any idea?
Option B, hard particles in workpiece.
Yeah, hard particles in workpiece causes abrasive wear. Okay, so uh, cold bond of chip with the workpiece. What does this result in? Cold bond of chip with workpiece. So, what does this result in? So, if the chip is cold, not the cold bond of chip with the workpiece, but the cold bond of chip with the tool, it is. So, cold bond of chip with the tool, it results in some fraction of the tool being taken away as the chip gets removed. Okay, so it results in adhesion wear. Okay, that ultimately results in crater wears on the surface of the tool. Okay, so chip carries away a portion of material from tool. This results in, this is called adhesion wear. Okay, Now, abrasive wear, so hard particles. So when hard particles come in contact with the, so hard particles in workpiece. So hard particles in workpiece, when they form chips, the chips will also, since chips are forming from the workpiece itself, their chips will also carry hard particles. So these hard particles will have a rubbing action on the tool surface. Okay, resulting in this abrasive wear. That is, due to the rubbing action, they will take away, they will like cut away few like very minute sections from the tool surface, and this results in abrasive wear. So hard particles in workpiece come to chips with hard particles, rubbing action on tool surface, resulting in abrasive wear. Okay, then oxide layer formation. So oxide layer, how does this form? Oxide layer formation happens due to chemical reaction, between the tool and the workpiece. So this process entirely happens at an elevated temperature. At that elevated temperature, there might be some chemical reaction happening at the tool surface. Okay, at tool surface, resulting in formation of oxides. Okay, now there will be an instance, there in some cases the oxides are harder than the tool material itself, but in some cases the oxide will be the particular oxide of the material is softer than the tool material itself. So if oxide is softer than tool material, then it will easily get removed. Okay, yeah. So now, softening at high temperature. So softening at high temperature results in basically a plastic deformation of the tool, or deformation of the tool, resulting in a softening of the cutting edge of the tool. So the tool will basically become blunt. Okay, softening at high temperature means plastic deformation. So cutting radius increases. Cutting radius or nose radius increases. Okay, so the force will also increase and the tool will become blunt. Okay, so this the correct option for this one is option number B. Now the next problem, the natural logarithm of the cutting speed varies with the natural logarithm of the tool life as a decreasing linear line, an increasing linear line, line with decreasing slope, or line with increasing slope. So can you give me the answer to this? Before that, can you tell me how the cutting speed varies with the tool life? What is the famous equation that we use?
Yes, sir. Taylor's law.
Taylor's equation.
Yes.
Taylor's equation.
So by Taylor's equation, Taylor's tool life equation, if we use, then that is V t to the power of n is constant, where V is the cutting speed and T is the tool life in minutes. Now, if we take a natural logarithm on both sides, okay, taking natural logarithm, what is natural logarithm?
बेस ई रहता है जिस बेस 10 सॉरी
Base E. The base E is called natural logarithm. Yeah. Okay. So that is ln we will take. V plus n ln t is ln c. Okay. So we are asked to plot the natural logarithm of the cutting speed with the natural logarithm of tool life. So how does this vary? So natural logarithm of the cutting speed is equal to minus n ln t plus ln c. So y is mx plus c. If we take it similar to this equation of a straight line, then we will get ln v ln t. Okay, and since the slope is negative here, so it will be slope is negative but the intercept is positive, so intercept will be somewhere on the positive ln v axis and the slope is negative, so it is like this, a line like this. Okay, so it is a decreasing linear line. Okay, that is decreasing linear line. So the correct option is option number 8. Okay. Now the next question, the segmented chips are formed in machining of which of these? So when is the segmented chips formed? Can anybody give me the answer to this? Or what are segmented chips? Any idea? So what are segmented chips? So we you know about different kinds of chips, right? So this is say continuous chip. Continuous chip. Then there are discontinuous chips. These are discontinuous chips. Then there are continuous chips with built-up edges. Continuous with built-up edge. And the last one is of segmented type. So how does the segmented chip look like? So a segmented chip, it basically looks like this. Okay, so what happens in a segmented chip is that it resembles a sawtooth. Okay, the tooth of a saw, in which there are regions of alternate regions of high shear and low shear. High shear region, and this is low shear region. Okay, so see in high shear region, since the shear is more, so the deformation will also be more. So compared to the thickness of the uncut chip thickness, that is T naught, the deformation in this section will be much more than T naught. whereas in the low shear region the deformation will be a little bit bigger than the T naught value. Okay, so this is what is segmented chip. So the segmented chips are found for the machining of difficult to machine materials or hard to machine materials like nickel alloys. Okay, like nickel alloys or titanium alloys. So difficult to machine materials, if it is done at a higher cutting speed, okay, then segmented chips are formed. Okay, so segmented chips are formed during machining of hard to machine materials at high cutting speeds. So the correct option is option number D, hard to machine materials at high cutting speed. So is it clear to everybody how segmented chips
Yes,
are formed?
sir.
Okay, they are also called serrated chips. Okay, so segmented chips are also called serrated chips. So don't get confused if another name is mentioned. Serrated chips, and the structure is called sawtooth type chip. Okay, okay. So now coming to the next question, the resultant of Fs and Fn should be uh, mm, uh, related to the resultant of F and N in which way? Like they should be, what are the conditions for the resultant of F, S and Fn in relation to the resultant of F and N? Can you tell me the answer to this? Can anybody tell me the answer to this? Yeah, can anybody give me the answer to this? What is Fs? What is the value? What is Fs denoted for?
The shear force,
Yes. So Fs is the shear force. And what is Fn?
normal force.
Yes. So the normal to this force. Say we are writing in this direction. Okay. Fn. Then the resultant of these two, okay, will be somewhat like this. Okay. Now similarly at the interface of the chip with the tool, the friction is working. Okay. So there is friction in this direction, and there is a normal force in this direction, such that F is equal to mu n. Okay. and that is mu is equal to F by N, and that is equal to the friction angle tan beta. Mu is the coefficient of friction, and beta is the friction angle. So the resultant of these two will be in this direction somewhat. Let be R dash. So what should be the relation between R and R dash? Can you tell me what should be the relation between R and R dash? It is related to the merchant theory. So can you tell me what is the relationship between R and R dash? See, when the chip is formed, there should be dynamic equilibrium. Dynamic equilibrium, that is the equilibrium of the forces involved. Okay, that is there should not be any resulting couple or resulting force or resulting couple because of the acting forces. Then only the entire process will be in a dynamic equilibrium condition. So for that to happen, the resultant of Fs and Fn should be equal in magnitude to the resultant of Fn. They should be in opposite direction and they should be acting along the same line, not along parallel lines, because if they act along parallel lines, there will be no resultant force, but there will be a couple, that is there will be a rotation effect. But if they act along the same line, then they will exactly cancel each other. So R and R dash should be equal in magnitude, opposite in direction, and along the same line. Okay, so the correct option is option number C. Okay, is it clear to everybody?
Yes, sir.
Okay. So Fs, Fn, F and N are all intrinsically acting forces. We cannot measure these forces by any means. Okay, but we can measure the cutting force and the thrust force, that is Fc and Ft. So the merchant has established these forces Fs, Fn, F and N in terms of Fc and Ft, and the shear angle and the friction angle. So, sorry, in terms of the Fc, Ft, the shear angle and the rake angle. So, that is how, and Fc and Ft can be measured using a force dynamometer. That is how we can measure the values of Fs, Fn, F and N. Okay. Now, how does lubrication affect the shear plane angle? Can you give me the,
So,
yes?
in the previous question, that Fs is actually shear force, and can you say that F is actually which force?
Uh, Sorry, can you please repeat the question? Fs is the shear force. Yeah.
Fs is actually shear force, and Fn is the
Normal to the
normal
shear
force
force.
along that shear.
Yeah.
And
No.
the other in the other diagram there is a force F, isn't it?
Yeah, this is F. Let me just write. This is F and this is N. So F is the friction force. There will be friction as a chip moves along the surface of the tool. There will be friction between the chip and tools, right? So that is the force, friction force. Friction force between the chip and the tool. And whenever we say a friction force, there is always a normal force associated with it, right? By the relation F equals to mu n. So that is a normal force associated with the friction force.
So, and this the resultant of these two forces should be along perpendicular. Otherwise, there will be slipping. What will happen?
The resultant of the two forces, which two forces?
R and R dash.
They should not be perpendicular. The R and R dash, whatever be their directions. See, this is a very arbitrary diagram. The R dash can be in this direction also, can also be in this direction R. Okay, and R dash can be in this direction, whatever be the directions. Okay. But essentially what should happen is that if this is R, then this should be R dash. That is, they should be equal in magnitude, opposite in direction, and they must act along the same line. Because if R acts along this line and R dash acts along a parallel line, then there will be a resulting moment or couple of the two forces.
Okay, sir.
Yeah. So is it clear?
Yes, sir.
Yeah. Okay. So yeah, let's go to the next problem. So how does lubrication affect the shear plane angle? So Merchant has given a relationship between the shear plane angle, the rake angle, and the friction angle. So do you know what relationship that is? Can anybody tell me what relationship that is?
सर फॉर्मूला पूछ रहे हो आप?
Yeah, formula पूछ रहा हूँ.
सर π/4 -1/2 ब्रैकेट में बीटा माइनस अल्फा.
Pi/4 minus, sorry, pi/4 plus.
π/4 -1/2
Hmm.
ब्रैकेट में बीटा माइनस अल्फा.
Okay, yeah, correct. So according to the Merchant's theory, the shear plane angle phi, it is given as 45 degree or pi/2 minus beta minus alpha half of this. Okay, which can also be written as 45 plus alpha by 2 minus beta by 2. Okay, so how does lubrication affect this shear plane angle? Any intuition about this? Can you give me any idea about this? How the lubrication is affecting, by which way will the lubrication affect the shear plane angle?
Sir, alpha is the rake angle.
It will affect
Sir, alpha is it rake angle?
alpha.
Yes, sir.
Okay, but alpha is the rake angle, right? Alpha is the rake angle. Rake angle is fixed for a tool. It is fixed for a tool. How will lubrication change it? A particular tool, if you are using, then alpha will remain fixed. Lubrication will not be changing it. See, with the use of lubrication, the friction will increase or decrease.
Decrease.
Yes. So friction decreases. Then see, beta is equal to tan beta is equal to F by N. Now F is decreasing. So beta will be, just consider from 0 to 90 degree itself. So if F is decreasing, then beta should decrease or increase. if f is decreasing, then beta should also decrease. This is beta, this is f, and this is n. The smaller beta, the smaller the value of f, the lesser will be the value of beta here. So in this equation now, if beta decreases, then what will happen to phi? If beta decreases, what will happen to phi?
Phi will increase.
Yes. So phi increases. And what have we seen? If phi increases, then the shear plane angle, that is, if the shear plane angle is increasing, then the shear plane length decreases. That is how the power required for the chip formation will also decrease, because the area, the shear area will decrease. Okay, so that is how lubrication decreases the power consumption. Okay, so the correct option here is B. So is it clear to everybody? If there is any doubt, you can ask.
So this shear plane angle increases, then what will be the effect on that cutting?
If the shear plane angle is,
Increasing, then the it would how it will be aiding the cutting.
see, basically the shear plane angle is this angle. This angle. So if the shear plane angle is this, okay, then the shear length will be this, ls. Okay, and if the shear plane angle is increasing, then it will be ls dash. Now, since ls is greater than ls dash, the width is the same, so w multiplied by ls is greater than w multiplied by ls dash. So in this case, the area, the shear area that we take, the shear area of the chip, which is something like this, the shear area with the width, this shear area will be greater than the shear area had the friction angle been higher. So as the shear area increases, what happens is that tau multiplied by shear area is the force required, right? This is the shear stress. Tau is the shear stress multiplied by the shear area will give the shear force required. Is greater than tau is dash. So the force required for shearing in case of a lower value of the shear plane angle is greater than the force required if the shear plane angle is larger. So yeah, tau is dash, and this is fs is greater than fs dash. So the power consumption increases if the shear plane angle is reduced. So if the shear plane angle is increasing, then the power consumption will reduce. So is it clear to you?
Yes, sir.
Okay.
So one more thing, actually, you said that the rake angle will be constant for a cutting tool, but actually, we can vary the rake angle state by changing the tool position.
Yes, but what I am saying is that obviously if you change the tool positioning with respect to the workpiece, the rake angle will obviously change. What I meant is that for a particular cutting operation, when we are doing a particular turning operation, we won't be changing the positioning of the tool or the angular positioning of the tool repeatedly, right? It will be at a fixed position attached with the lathe machine. In that case, if the angle of the tool, if the angular position or the basic physical position of the tool is remaining fixed, in that case, with respect to the workpiece, it is remaining fixed. In that case, the rake angle will remain fixed. It is not obviously it is always the rake angle. All these angles are always in respect to the relative position of the tool with the workpiece. So if the position between the tool and the workpiece changes, then it will obviously change. But we are considering that during a cutting operation, the tool is not changing its position relative to the workpiece. In that case, the rake angle will remain fixed.
Okay, sir. So while during a single operation, it won't be changing.
Yeah, in most of the single operations, like or even repetition of like repetition of operations also, like we would like to keep the rake angle fixed for a particular turning operation on different phases. If the turning operation itself is changing, or that turning operation or a different kind of turning operation is required, then obviously we will have to change. Suppose from turning to finishing, then we have to, in the finishing operation, we will have to keep the tool exactly perpendicular so that it can directly cut through the workpiece to remove the part for parting of operation. So that is what, like, depending on the operation it will change. If even if the same operation, even if the same kind of turning is being repeated, then also essentially or in most probably I would say that the rake angle or the tool will remain fixed, and tool positioning will remain fixed.
Okay, sir. So in the single cutting operation, only the one point of the tool will be contact with the uh, workpiece, or in that there was an edge cutting tool for edge cutting. There's an edge for cutting, isn't it? So will that be working during that single cutting operation, single point operation?
Just can you please repeat? You told me that a single point cutting tool, only one point will be in contact with the workpiece.
Yes, sir.
Yes.
But when we look at the tool, actually in the nomenclature, there was a edge cutting angle for the tool, isn't it? So will that be contacted in that process for
See,
single point?
single point cutting tool does not mean that one single needle like point will be in contact with the workpiece. Okay, the entire cutting edge, that is, a entire cutting edge like this, will be in contact with the workpiece. A entire cutting edge like this will be in contact with the workpiece. That is how a chip can be formed. If a pin like structure like this is in contact with the workpiece, it won't be generating a chip with a area that we are considering, right? The entire cutting edge has to be in contact with the workpiece. It is called a single point cutting tool because it has only one such cutting edge. That is why it is called a single point cutting tool. It is not a
Oh,
point necessarily.
okay, sir. So actually, it will be in a radius point, in nose position for that.
Yeah, in the nose position, but the nose position is not essentially doing the entire cutting operation. The cutting edge along with the nose is where the tool will come in contact with the workpiece. The nose radius is given such that nose radius along with the um angles at the end cutting edge are given so that there is a gradual contact of the tool with the workpiece, but the cutting action will take place from the entirely from the nose with along with the cutting edge. That is why it is called the cutting edge.
Okay, sir. So,
Yeah,
in the figure that have you drawn at the top, there was a while during the turning operation, we'll be viewing it from the top position. How that top position is becoming that the figure in the right side. I mean, when we are viewing it from the top, the shear plane will be the chip will be moving at the top of the tool, isn't it?
yeah, yeah, yeah.
But yeah, the image that given here is actually we are chipping off from the uh, top of a sheet, isn't it? So how
Yeah,
will
so supposedly if we draw a something like this, okay, sorry, something like this, and this is the tool. Okay, now just a minute, let me rub this things and make some area, otherwise it is getting difficult. So yeah, so suppose this is the workpiece and this is the tool. Now when the turning happens, something like this, if we enlarge this section, we will see that something like this is coming up from the chip, and this is the tool which is in contact with it from the sorry. When we see this section enlarged, we will see that this is the workpiece, the chip is coming off like this, okay, and uh, this is the tool, this is the tool, this is the tool. Now if we see this from this side, from this side, if you view it, won't this look similar to what I have shown here?
Yes, sir.
Yeah, so that is how this comes.
When we view it from the turning position, actually the chip will be the we'll be viewing it from the top for that right figure, and the chip will be
This
going
is
up.
essentially a side view. Whatever we are seeing here is a side view.
Okay, sir.
Yeah, so like whatever we have drawn here is a side view. From the top view, if you observe, you won't be able to see what is the sheared plane or how the shearing is happening. So this essentially is a side view. Okay.
Okay, sir.
Yeah. So is it clear to you?
Yes, sir.
Okay. Okay. So should we move on to the next problem?
Yes, sir.
Yes.
Okay. Yeah. I appreciate that people are trying to interact, because this is the basic, uh, you know, objective of this interactive session. So I am happy that students are trying to interact. So please do ask questions. If you have doubt, do ask questions. So with increase in the cutting speed, the temperature at the chip tool interface increases because friction increases, the mm, lubrication fails, tool does not get time to carry the heat, or chip removal becomes difficult. So can you give me the answer? Can anybody please give me the answer? Any idea? Yeah, somebody has an answer.
So friction increases.
Okay. Uh, any other answer?
Sir, I
So
think
I think
option C. Option
yes,
C.
see.
Option?
Sir, option C. Tool doesn't get time to carry heat.
Yes. So essentially, during with the increase in the cutting speed, the friction actually decreases. It does not increase, because you see that the greater, if you consider friction as a resisting force, so basically with the increase in cutting speed, that the tool or the workpiece, they are trying to overcome the friction. uh, as a result, the speed increases. So the friction basically, with the further increase in the cutting speed, the resulting friction between the tool and the workpiece, or the chip and the tool, will decrease. Okay. uh, the lubrication might fail because of the increasing temperature, but that is not essentially the case. The temperature at the chip and tool interface increases because the tool does not get enough time to carry away the heat, because the contact time between the chip and the tool decreases with the increasing cutting speed. That is why the tool does not get sufficient time to carry away the heat. Contact time between tool and chip decreases. So tool does not get time to carry away the heat. So the correct option is C. So temperature increases. Okay. Now the next question: the Sardmates tool inserts are manufactured by which of these? Yeah, so Sardmate tool inserts are manufactured by which of these? So the correct option is D, powder metallurgy. So Sardmate tool inserts are basically something like cobalt and tungsten carbide, stuff like that. Cobalt with tungsten carbide. So these two components mixed together in the powder form and then manufactured using powder metallurgy is the way these Sardmate tools are produced. Okay. So because we need a combination of two or more elements, that is two or more composing elements, so the powder metallurgy is one of the most suitable techniques for making Sardmate tool inserts. Now coming to the next question, we are trying to solve some questions related to the basics of grinding process now. So in grinding process, the glazing and loading are which of these? What is glazing and loading? So glazing refers to blunting of cutting edge of abrasives and loading. Loading refers to the filling of chips and debris. Loading refers to filling of debris or chips in the space between the abrasives. So the correct option is option number A. Okay. So are these clear?
Yes, sir.
Okay. So the next problem. The correct choice of the grinding wheel as part of the work material is hard grade for hard material, hard grade for soft material, soft grade for soft material, or all of the above.
Sir, option B.
Yes, option B is the correct answer. But can you tell me why? Yes, so can you tell me why? Why do we need hard grade for soft materials? Or vice versa, if you give the answer to the opposite thing also is fine. Like, why do we use soft grade for hard materials? Yeah, I think
So for the soft material, it will be ductile. If you use hard material to grind it, it will be easy. And for the hard material, it will be brittle.
sorry, your voice is not actually clear as of now. Can you please repeat?
S For the soft material, it will be actually ductile, and when we use the hard grade, we can easily grind.
But why can we not grind a soft material using a another soft grade material? It is a, after all, soft material is okay. We are taking that it is ductile. Then the soft material can also, we should also be able to use it, right? Should be able to grind it.
If we use the soft material, it will deform.
The soft material will deform.
Yes.
But should not the soft material be deformed if the hard grade is used? First, tell me, do you know what is grade? What is grade?
Sorry, is it the grain size of materials in that grit?
No, that is a grit size. This is, that is not grade. Grit size and grit and grade are different. Okay. So what is grade?
Great are dense chorus. That's the type of grain size is there. No?
Mm, sorry, you said coarse or porous. I didn't get.
Chorus, dense, medium, soft, like that.
Okay.
Three categories are there.
Okay. Yeah. So
So
not that.
grade is strength of the bond,
Yes.
bond type.
Yeah. So grade is basically not coarse or fine grain structure or medium or soft structure. It is basically the strength of the bond between the grinding wheel and the abrasive. Okay. Strength of the bond between the grinding wheel and abrasives. Okay. Now tell me, is, do you want to change the answer? Like why hard grade is used for soft materials, or why soft is used for hard materials? See, what happens is that, let us first go for hard materials. So for hard materials, abrasives wear out easily. So when abrasives wear out, they should be removed. Otherwise, the entire grinding wheel will become blunt. So easy removal of abrasives become essential. Okay. Easy removal of abrasives become essential. That is why if we take a soft grade material, a soft grade grinding wheel, then soft implies that the strength of bond between the grinding wheel and the abrasive is less. Okay, that it is, you can say that it is loosely attached comparatively. That is why the ease of removal of the abrasives from the workpiece, sorry, from the grinding wheel becomes easier. That is, the removal of abrasives from the grinding wheel becomes easier, so that once the abrasives are removed, then the next layer of abrasives can start the machining. Okay, so soft grade is used. Now for soft materials, abrasives remain sharp for longer time, longer usage, longer usage time. Since the material is soft, so the abrasive will not wear out easily, right? So if the grade is soft, then they will be removed easily. That is, we are losing abrasives which are still sharp, that is, which can still perform the cutting operation. So we won't be using soft grade, but we will use hard grade, so that these abrasives which are remaining sharp can remain attached to the grinding wheel and continue the cutting operation. So abrasives should remain attached with a grinding wheel. This implies hard grade should be used. So is it clear to you now why hard grade should be used
Yes, sir.
for soft materials? To everybody, is it clear to
So
everybody?
if actually for the staying using the grinder for grinding wheel for more time, I mean
Yes,
the main.
yes,
Okay,
yes.
sir.
uh, um, for using the grinding hill, not for using the grinding hill for a longer time, but for using the same layer of abrasives for a longer time, because the abrasives will retain their cutting, the sharpness of their cutting edges if the material is soft. It is not for using the grinding hill for a longer time. It is for using the same layer of abrasives for a longer time, so as they already retain their sharpness.
Okay, sir.
Yeah. So the correct option is option number B. Now coming to the next problem, most desirable feature of a cutting fluid is which of these? High viscosity, high heat transfer ability, ability to reduce the shear force, or easy to handle?
Ability to heat transfer ability.
Yes. So the specific heat and the heat conductivity of the cutting fluid should be high. Okay, so that with a lesser amount of cutting fluid only, a larger amount of heat can be taken away from the interface, whatever interface we are considering. If it is high viscosity, then it will be difficult to flow, okay, easily. So the correct option is option number B. Now, the next problem, the flooding method of cutting fluid application is used in which of these? Low speed cutting condition, high speed cutting condition, brittle materials machining, or ductile materials machining with high speed?
Ductile material with high speed.
Okay, but why ductile materials with high speed?
Ductile material is going to increase that chip size, no,
Yes, chip
and
size will
heat.
increase, but why flooding method?
Brittle material
Sorry, sir. Sorry, sir.
Okay,
brittle material machining.
brittle material machining. Okay, it is not necessarily a materials condition, it is basically a speed condition. So see, what happens is this flooding method, it is a non-pressurized method of lubricant application. Okay, that is, the lubricant is not pressurized in this case, a lubricant or the cutting fluid of cutting fluid application. Okay, and there is another type which is called mist method. Okay, so it consists of pressurized air plus atomized cutting fluid. Now, when there is an interaction of the tool and the chip in this direction and with the workpiece here, if it is moving at a high speed, okay, then the space, then the ease of the movement of the space, sorry, the ease by which the cutting fluid can move into these spaces is difficult or easier, like with which the cutting fluid can reach these places if the cutting that is the cutting speed is high. What I am asking is, if the cutting speed is high, then the um, cutting fluid can reach these small places easily or with difficulty.
No, sir. No, sir. No, sir. It's difficult to reach.
Yes. So when it is a high cutting speed, then we will require a pressurized condition to because such that with pressure, that is with an added force, it can reach this difficult to reach small places. But if the cutting speed is low, then with ease the cutting fluid can reach these places between the tool and the chip and between the tool and the workpiece. That is why for low speed cutting condition, the flooding method, because it is non pressurized, so for low speed cutting condition, the flooding method is used. Okay, so
Okay.
yeah, so the flooding method,
So,
yeah.
so for the brittle materials like stainless steel and machining of the such kind of steel, the heat will be generated more, isn't it? So, do we use the flooding for uh, machining of that kind of materials? I mean, the heat generation will be very high, isn't it, for the stainless steel materials?
Stainless steel, sorry, stainless steel.
uh, Stainless steel products for machining such products will the if we do more time, the heat generation will be higher for that kind of brittle material, isn't it? Hard and brittle material. So do we use that flooding method for
But
uh,
stainless steel is not brittle material.
so it's actually martensitic. I mean, it's really hard, isn't it?
See, like if you are trying to focus on the hard and brittle materials, you can say high carbon steel. Whatever be it, the condition that you are trying to say is that for brittle materials, the temperature is more, so the flooding should be used. But flooding does not mean that a flood of cutting fluid is actually in operation. See, even if you dip this entire cutting zone into a like into a barrel of cutting fluid, only a fraction of the cutting fluid will reach this zone. Okay, so whatever cutting fluid it will reach this zone, okay, and this zone, these two zones will be the one in our application. It does not matter how much, like how much of the cutting fluid you are applying, if they do not reach this zone. So if at a high temperature condition, if you feel that it is like a choice, okay, if you feel that for high temperature conditions, high temperatures are also attained during high speed cutting conditions also. So if you want that the heat removal should be facilitated, then you can use mist method. But the flooding method, it does not necessarily mean that there is a flood of lubricants. It is a non-pressurized application of cutting fluid, like a what we can say that it is a natural flow. Okay, natural flow of the cutting fluid into the cutting zone. Okay, in that cases, even if a high temperature situation is happening for the machining of some particular application, whatever it is, some high temperature is attained within the cutting zone, then also the flooding can be or may not be beneficial depending on what is the cutting speed at that situation. If it is a low cutting speed situation that is generating some high speed because of some other reason, maybe because of the bluntness of the tool, or because of friction, larger value of the friction between the tool and the workpiece material, whatever it is, even if it is a low speed cutting condition, then we have to use the flooding method. But if it is a high speed cutting condition which is resulting in that high temperature in the cutting zone, then we have to use a mist method. Okay, so please do not confuse the flooding method with a flood of lubricant. Okay.
So this flooding method doesn't mean that it will be dipped inside
No,
the
no, no,
material.
no, no. Have you seen any like in the lathe? You have seen machining in the lathe. Have you
Yes,
seen?
sir.
So
Yes,
did you see any cutting zone being dipped in a barrel of
sir.
cutting fluid? No. So that
No.
is not how it practically happens. You either pour the lubricant using a small jet, it is not that much pressurized, or you apply a mist using this pressurized air and atomized cutting fluid. Okay, so it is not that dipping in the barrel. It does not happen. Okay.
Okay, sir. So in that CNC machining, actually, it will be sprayed onto the metal, isn't it? Or it will be the jet will be used, isn't it? So does that mean if it is pressurized, then it will be mist, and if it is not pressurized, then that means it's actually flooding method.
If it
Is it
is, sorry, your voice was not clear again. If it is,
I mean, for the CNC machining operations, like if actually it is the jet is impinging on this machining workpiece, isn't it?
hmm,
So, if it is pressurized, then we can say that it is mist, and if
yeah,
it is
yeah,
pressurized, then we can say it is flood.
yeah, essentially if it is if pressurized air is used for the application of the cutting fluid, then it is a mist method, and if not, then it is flooding method.
Okay, sir.
Okay. Okay, so yeah, now grinding of the hard materials require abrasives of fine grit size and higher grades, fine grit size and soft grades, coarse grit size and hard grades, or coarse grit size and soft grades.
Sir, I think option B.
So you were saying fine grid size and soft grades. Why? So soft grades we have already discussed. Why fine grid size?
Sir, because we are taking soft grade, so I think for soft grade we need to find grid size.
How is soft grade related to fine grid? I already told you, right, that grid is not equal to grade.
So for the fine grit, the point of application force will be higher.
Sorry, for fine grade,
The point of application force will be higher, isn't it?
which force?
The grinding force.
Yeah, so the grinding force will be higher for fine grade. Is it so? Is it the reason why grinding of hard materials is done with fine grid size?
I mean, for grinding the hard material, we need to apply more force in it. So if we can apply more force using the fine grit, then
How is more force related to fine grit?
the area of contact will be lower, isn't it? When we use a coarser grit, the area of contact will be higher.
Okay, so you are basically talking about the contact area, not the hard material. So
Yes,
even
sir.
if for a soft material, if the area is large or small, it will decide if it is finer grit or soft grit. It is not with the hard material. It is not related to hard, just the material condition being hard or soft. It is the area. Okay, so why steel? The fine abrasives are used for hard materials. This is not the correct answer. Yeah, what I mean to say is that you are saying for a larger area, the fine grit size will be like a finer grit will mean more abrasives and hence a more distributed area on which the force can be applied. But for a for soft materials also, if the area is such that it will require a fine grit size, then we will have to use. Okay, so it is not essentially the hard or soft. The area consideration you are considering is just the area, the larger area or smaller area. And actually, for small, actually for smaller area, we will be requiring finer grit size. So again, why hard material requires fine grit? So this is coarse grit, okay, and this is fine grit. And this is coarse grit. Now, can you, by intuition, can you like think of a reason why for hard materials we are using fine grit?
So the surface contact will be more for the fine grit.
Sorry, for surface what?
Surface contact during the grinding.
Okay. Any other answer?
So is there any possibility the hard material will be having a small microstructure, isn't it? So
No, 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 no. Not possible.
okay.
Yeah. Any other? Isn't it intuitive? Think about this region. When it comes in contact, think about this region. This is how the material gets removed from here. And this is how the material gets removed from here. So think about this region. What is this? What is this called? What is this called?
So the surface finish will be higher for the fine grit.
But surface finish is a requirement. What is this? What is this called? What is this dimension called?
Depth of cut.
Yeah, depth of cut. So you can use higher depth of cut for a hard material or soft material.
For the higher, we can use the hard material for
Think again.
hard material will be hard to dip, the depth of cut will be lower. I mean, we need more force for if we use the coarse grit for the hard material.
Yes, exactly. So what happens is that the for for coarse grit, depth of cut is higher than fine grit. Now for hard materials, the depth of cut should be on the lower side for easy removal, because a hard material you cannot plow and remove so much of material at one go, right? You have to use extremely large forces, so depth of cut should be low. So for hard materials, we use fine grit size. And why do you use soft grit? We have already discussed previously. So the correct option is option number B. So is it clear to everybody?
Yes, sir.
Yes, sir.
Okay. Now a numerical problem. So a cast iron workpiece of dimensions length, width and height as 220 and 50 millimeter has been grinded with aluminium grinding wheel of diameter 150 millimeter and wheel width of 10 millimeter. The grinding velocity used is 6000 revolutions per minute. The table speed is 5 meters per minute. The depth of cut per pass is 40 microns and total number of grinding passes is 20. The average tangential cutting force, okay, is 70 Newton. The value of the specific grinding energy needed is which of these? So for the solution of these, let me first draw the schematic of the process. Okay, so this is 200 millimeters length. The width is 20 mm and this is the height is 50 mm. Okay, now there is a grinding wheel of diameter 150 millimeters and width is 10 millimeters. So there is a grinding wheel like this, okay, whose diameter is 150 millimeter and whose width is 10 millimeters. So in this direction, that is the width of the wheel, so it is 10 millimeters. Now the grinding wheel velocity is 6000 revolutions per minute. The table speed, that is the speed of this, the table speed is 5 meters per minute. The depth of cut per pass, this depth of cut is 40 micrometer and the total number of grinding passes used is 20. That is one pass of the grinding wheel, one pass of the grinding wheel like this, complete one pass of the grinding wheel from this point to this point. This is repeated for 20 times with each depth of cut being 40 micrometer. The average tangential cutting force is given as 70 Newton. That is FC is given as 70 Newton. Okay. So the value of the specific grinding energy we have to find out. So see if the diagram is clear to everybody. Is the diagram clear to everybody?
Yes, sir.
Okay. So,
So
yeah.
why the velocity is taken in the perpendicular direction? I mean,
Can you please repeat?
so why that velocity is taken in the perpendicular direction? I mean,
Velocity taking in the perpendicular direction? Which one?
the direction of that velocity is taken, isn't it? Why it is taken in this direction?
Which velocity are you referring to?
5 meter per minute.
Okay,
M-
so this is not the cutting velocity. Okay, the cutting velocity will be this one, that is in contact. Whatever is in contact with the grinding wheel and the workpiece because of the rotation at 6,000 rpm. That is, we have to find out the cutting velocity. This is with which the table, or the workpiece, this workpiece is moving in the lateral direction. That is, after one pass, or after like during the pass also, if it is a continuous speed, then during the pass also this table is moving at a speed of 5 meters per minute. Or after this pass is made, one pass is made, the grinding wheel remains in that position and the table shifts with a speed of 5 meters per minute, so that the next layer in the width direction, that is along the direction of 20 millimeter, the next layer can be cut using the grinding wheel.
Okay, sir. So actually, the each for each pass, 10 mm width of that grinding will be bit.
Yes, yes, yes. So we have entire CU, we have 20 mm. So there has to be a feed given in this direction so that the gradually that 20 mm can be cut, right?
Yes, sir.
Yeah,
So one more thing,
yeah.
actually, by meaning the feed motion, it's actually the movement of the workpiece or the movement of the tool.
It depends. Like in generally, the grinding wheel, this grinding wheel, if you have observed the working of a grinding in the grinding wheel for surfacing process or whatever it is generally the movement of the workpiece attached with the table. That is why it is said as table speed.
So there should be a movement for the wheel also, isn't it? Other than the rotation.
Sorry, other than the rotation, you said what?
There should be a movement for the wheel in that direction, perpendicular to the workpiece movement. So
No, supposedly, you see, supposedly the wheel was initially in in this region it was cutting. Okay. Now, if the wheel remains in this position and the cutting and the workpiece moves in this direction, then the next position of the workpiece will be this. So the tool will now be moving on a different plane, something like this. Okay. So initially it was cutting like this. Now it will cut in this layer.
yes, sir. The wheel needs to move forward, isn't it? There should be velocity for the forward movement for this wheel, isn't it? Then only,
Forward movement you are asking in this direction.
yes, sir, yes, sir.
Yeah, there is obviously a forward movement of the tool in this direction.
So can we consider that as a feed motion? We can confuse with that both movement, isn't it?
Yeah, it depends like which one you are considering. The table speed, you were saying that there has to be a motion in this direction, right? So yeah, that can also be. If we consider even that, then this will not be here. Like if we are considering the table feed to be in this direction, then we would have to say that for one pass only we are considering. That is, the grinding wheel is remaining fixed in this direction, and only this layer of material is being removed. Only one layer to a depth of 40 micrometers, and then again 40 micrometers in the same direction, in the same position. That is 40 micrometers here once, then again 40 micrometers here for 20 passes. So it will be like this only. So if we consider this, that is the 5 millimeters per minute in this direction, it will also be the same, but for one pass, 5 millimeters per minute.
Yes,
Sorry.
sir. So my doubt is actually when the question is given only the if the question is like the feed motion is this much,
Hmm.
then which should we take? I mean, the forward direction or in the table direction.
Okay. So what I am saying is that if the table speed is given, then like you can consider. Uh, uh, Sorry, I didn't get understand actually. What were you saying? Once again, can you please repeat?
I mean, if the in the question only the feet motion is given, the feet motion is like 5 meter per minute. Do we need to consider only one pass, or uh, uh, do we need to consider that motion as the table movement in forward direction, like for different passes?
Okay, so in this case, I think so. If the total number of grinding passes is given and if it is not mentioned as multiple passes here, so we can consider it in this direction. If it is mentioned as specifically as multiple passes, then we can consider that that is the table feet in the lateral direction. If what I am meaning to say is that if it is a multiple pass, it will be mentioned.
Okay, sir.
Yeah. So, so is the schematic clear to everybody?
Yes, sir.
Yes, sir.
Okay. So, yeah. So, can you tell me how can we find out the MRR? Any idea? Okay. So, see, first we have to find out the total depth till which the grinding is happening. So, there are 20 passes. So, the depth of cut per pass is given as 40 microns. Okay. So, total depth of cut is 40 multiplied by 20 micrometer. Okay, that is 8 into 10 to the power minus 4 meters. This is the total depth of cut. Now this is the depth of cut. This is the uh, width of the grinding wheel, and this is the total depth of cut. Okay, and this is say the feed here that we are considering to be 5 meters per minute in this case. So this is the area multiplied by this velocity of movement will give the volume that is removed per unit time. Volume removed per unit time. Okay, so that is how we get the MRR. Okay, is it clear to you how to find out the MRR here?
Yes.
Yeah, so MRR is basically the total depth of cut multiplied by the width of wheel multiplied by the feed rate, table feed. Sorry, sorry about that. Yeah, MRR is the total depth of cut multiplied by the width of wheel multiplied by the table feet. So total depth of cut is 8 into 10 to the power minus 4 meters multiplied by width of the wheel is 10 millimeters. So 10 uh, just a minute. Just a minute. Okay. Yeah, sorry. There is something wrong with the question. This dimension will be 20. This dimension will be 40. Or wait. Yeah, sorry. This dimension will also be 20. So the wheel width is 20. So there will essentially be only one pass. There will essentially be only one pass here. There is no chance of two passes. So this is 20. So yeah, 20 millimeters, that is 20 into 10 to the power minus 3 multiplied by the table feed is 5 meters per minute. So 5 divided by 60 for this is meter cube per second. 60 for conversion of minute to second. So MRR is equal to, so if we do the calculation, what it will be 8 into 20 into, so this is 3. Okay, so 40 divided by 3, 10 by 3 into 10 to the power minus 7 meter cube per second. Now this meter cube can be written as 10 to the power 9 millimeter cube per second. Okay, so it is essentially 4 by 3 into 10 to the power 3 millimeter cube per second, which is 1333.33 millimeter cube per second. This is MRR. Now till here, is it clear to everybody?
Yes, sir.
Okay, so the power required is equal to the cutting force multiplied by the uh, cutting velocity. What is the cutting velocity? So the cutting velocity is what I was referring to here. So this is the cutting, this will result in the cutting velocity, okay, which is given as pi dn by 60. Okay, so pi multiplied by the diameter is 0.15 meters multiplied by 6000 revolutions per minute by 60. This will be so this is 100. So this is 15 pi meter per second. So you put it here. The cutting force is given as 70 Newton multiplied by 15 pi. This will give it as watt. That is Newton into meter per second. Newton in meter is joule, so joule per second is watt. So the answer here is 3298.67 watt or joule per second. Now the specific energy consumption, specific energy consumption. The specific energy consumption is this power by the material removal rate. This basically denotes the power required for unit material removal rate. Okay, so power is 3298.67 joule per second, and this is material removal rate is 1333.33 millimeter cube per second. So it will give something in joule per millimeter cube, which is 2.47 joule per millimeter cube. Okay, so the correct option here is C, option number C. Okay, so is it clear to everybody?
Yes, sir.
Okay, so let me move on to the yes, is there any doubt?
Sir, one similar question is given in a assignment, but
Okay,
data is little bit different. But answer is not matching whatever that is given.
okay, so I suggest you to give the option as the closest answer. or if there is still some ambiguity, you can ask in the discussion forum, because the questions of the assignments are being set by the professor or the teaching assistants in the uh, the host institute, that is the teaching assistants at IIT Roorkee itself. Okay, so I am not certain about how to rectify about it, that. So you can either ask this or raise this doubt in the discussion forum, or you can mail the teaching assistants. That will be helpful. So it's fine, right? Like it is clear to you what to do, right?
Yes, sir.
Yeah. So coming to the next problem, the most suitable abrasive material for grinding steel and cast iron is which of these?
Silicon carbide.
Yeah, silicon carbide. So silicon carbide is basically used for cast iron, for brittle materials, and some other steels like that, for such other steels which are like kind of brittle. For high strength alloys, for aluminum oxide is used for high strength alloys. High strength alloys and high strength steels. That is high strength steels, that is which will have a significantly higher yield strength and maybe higher toughness. Okay, then diamonds are used for ceramics, glasses, cemented carbides. Like these are used for tools. Okay, and cubic boron nitride or CBN. Okay, it is used for tool steels and cemented carbide. Okay, so
So
yeah,
in this, which one is having more harder? I mean, for the AL203,
hmm.
the high strength alloys are, you said that. So by meaning the high strength alloy, does that mean that they are brittle? I mean,
No. High strength alloys does not mean brittle. High strength alloys means their yield strength will be higher. That is, they will deform after being subjected to a higher value of stress. Okay, and high strength alloys generally, that is those which have higher value of yield strength, if they are not brittle, then they have also high toughness. That is, they will undergo plastic deformation significantly. Okay, like the ductile materials. Okay, so
okay, so
strength is
can they
not.
be ductile?
Yeah, yeah.
Can we say they are ductile material or high strength?
Not necessarily. If the toughness or the plastic deformation zone is high, then the material will be ductile. Okay, see, if the this is the this is corresponding, this is a low strength alloy, this is a high strength alloy. Okay, so if this is this plastic deformation zone exists, then it is ductile. And if the stress strain curve is something like this, does this, just this much, okay, then it is not ductile. There will be fracture immediately after the yielding, so that is not ductile. So you have to know the exact stress strain curve to say if the material is ductile. If the material is having high strength and toughness, then it can be a ductile material of high strength. Okay, if the material is having a high toughness, then it is essentially ductile. It is not correlated in that way.
Okay, so if the yield point is higher, then we can say it is a high. It have high strength.
Yeah, high strength, because at higher value of the applied stress, the material will start deforming. After it starts deforming, it may undergo plastic deformation significantly if it is a ductile material. If it does not undergo plastic deformation significantly and breaks, then it is a brittle material, like eggshells. Eggshells have high strength, but they break immediately after a particular point. They break immediately. So that is a example of a comparatively high strength alloy with which is brittle. Okay.
Okay, so but for the tool steel, it will be actually brittle, isn't it? The tool steel will be breaking suddenly, so it's actually a brittle material, isn't it?
Yeah, tool steels are generally hard and brittle. Hard and brittle. Yeah.
So can we say that for the brittle material, CBN can be used, but for the steel and cast iron, they are also brittle, but we are using silicon carbide. Is it due to the cost of machining or anything we are?
No, no, it depends on the relative hardness. CBN, CBN basically has much higher hardness than silicon carbide. CBN hardness is in the range of 4000 to 5000, whereas silicon carbide is in the range of 2000. So, depending on what hardness is there, like tool steels are much higher than cast iron. Okay, so that is why silicon carbide can be used for cast iron or brittle steels, but CBN can be used for much harder, not essentially brittle material, much harder steels such as tool steel or cemented carbide steels, the cemented carbide tools.
Okay, sir. So if we are arranging the these four materials in the based on the tool life, then how it will be? I mean, the diamond will be having higher.
That depends, like what cutting conditions are you putting into, but in general the diamonds have much higher tool life. But if you use the diamonds with tool steels or diamonds with uh, mm, some ferrous alloys, okay, such as steels, okay, in that case what happens is that there is a chance that the diamond will start to get degraded, because the iron in such ferrous alloys have an affinity for the carbon of the diamond, so it will start to diffuse to the tool region, and that is why it will start to wear out. So it depends which what you are using the diamond with, but in general if used properly then the diamonds are having the maximum tool life, I would say.
Okay, sir. So for the alumina and diamond, the cost will be higher.
For alumina, what?
So for the high cost material, which one, diamond or alumina?
For high cost material, uh, I don't understand this, like the material property will decide if it is alumina. If it is a high cost high strength alloy, then we will use alumina. If it is a high cost ceramic, then we will use diamond.
Okay, sir.
So cost of the workpiece material is not the factor here. The property of the workpiece material is a factor here.
Okay, sir.
Yeah. So should we move on to the next problem?
Yes, sir.
Okay. So a grid size of 100 refers to which of these? This is a very simple question. So tell me, grid size of 100 refers to which of these?
So medium.
Any other answer? I don't think it is medium. See, 8 to 30, it is coarse. 30 to 60, it is medium. 70 to 200, it is fine. And greater than 200 till 600, it is very fine. So the correct option is 100 will refer to C, fine abrasive. Okay.
Okay, sir.
Yeah. Now the next question. Uh, this we have already discussed. With hard workpiece, soft grade is used for which of these? We have just discussed this a while back. Why is soft grade used with hard workpiece?
Removal of abrasives easily.
Yes, removal of abrasives easily. Yeah. Now the next question. So compared to milling, grinding has which of these? The power consumption and speed of rotation that is relative to milling. The grinding has which of these?
सर ए और बी में से एक आंसर होगा शायद.
So higher power consumption, lower speed.
Higher power consumption and lower speed. Okay. So have you seen a grinding operation and a milling operation?
Yes sir,
So
I have seen.
in the milling operation, it's actually multi-point, isn't it?
Yeah, multiple. But have you seen the speed of rotation of a milling tool, milling cutter?
Yes, sir, it will be higher.
It will be higher. Have you seen the grinding operation rotation?
Yes, sir.
So you think the milling still has a higher value of rotation?
Grinding has a higher speed of rotation, but I'm confused in the power consumption.
Okay. So what is the uh, what is the range of the speed for milling operation?
Sir, it depends on indexing.
It will depend on indexing, but what can be the maximum value? Like what is the maximum value around, like about that? Like there will still be a range, right? So the milling operation is carried out in general to a speed of around 200 to 250 revolutions per minute, but the speed can go till like 1000 maximum, 1000, 1200, something like that. But grinding, mm, yeah, 1000 revolutions per minute in vertical milling machine. Yeah, that's what I am saying. So it is maximum around 1000. But grinding has a general speed of around 5000, 6000 revolutions per minute. In the previous problem that we have solved, it was 6000 revolutions per minute. So grinding has much higher speed of rotation as compared to milling operation. Okay. And uh, power consumption. So the material removal is higher or lower in grinding?
Sir, higher.
In grinding,
Lower.
yeah. So material removal in grinding is lower than, see, in if you observe milling operation, you can see the chips very easily. Okay, whatever comes out as a chips, you can see them. But in grinding, you will see the chips are basically, you will see as dust particles. Okay, so very fine grain like grains will come out. So that is how small is the material removal in grinding than milling. And if we consider the specific power consumption, okay, is equal to the force by MRR. So we are seeing that if the force is still the same, then MRR is lower for grinding, much lower actually, much lower than MRR for milling. So the power consumption for grinding will be much higher. Specific power consumption for grinding is much higher than specific power consumption for milling. So this is one, and the speed of rotation in grinding has is always higher than milling. So which one is the correct option?
Option option B.
Yes, option B. In grinding is much larger than speed of rotation in milling. Yeah. So the correct option is option number B. Okay.
So, but since the material removal is higher for the milling, I mean, we need to apply more force, isn't it? So, the for consumption should be more for that milling, isn't it? Instead of grinding.
See, we are doing the milling operation with a tool something like this. Okay, the rotation we are giving a power, particular, just whatever power you say, suppose P. And for grinding we are using this kind of cutters for this one, for the removal. The same power is used for rotating. It does not, we are not concerned with what the tool size is. We are just rotating the cutter at a particular speed. Now for this one, the material removal will be occurring at a higher depth, and for this one the material removal will occur at a lower depth of cut. Okay, you may say that for higher depth of cut the power consumption will be higher, but what I say is, we have discussed this in the previous class, that if the depth of cut is reduced, then this, suppose a for this thickness, for a thickness something like this, it is removed once, the power is P. And if this same thickness is reduced like this in layers like this, then the power, if for layers the power is P dash, then this P dash will be greater than P, because for every layer removal the friction force will be the same. Friction force for this removal, this is the area that is in contact with the tool, so the friction force is F. For each layer here there will be an F, F and F, every time there will be an F. So the total power consumption for this P dash, the sum of all removal for this individually they might be lower, but the total power consumption for each individual layer, okay, will sum up to P dash, which will be higher than B, because for each layer there will be friction acting, which will be the same as for one single layer removal. Okay, that is why the power consumption for grinding is much higher than that of milling. Okay.
Okay, sir. So we need to don't need to confuse with the CNC milling machines are like it's a huge machine, isn't it? So it will be consuming larger power comparing to the smaller grinding machines.
You were saying that the CNC machines are having a larger power than the smaller grinding machines. That's what you were saying, right?
Yes, sir.
The thing is that if the same for this, you have to consider, if the same workpiece is being machined to same depth by both these machines, then the total power consumption will be much higher for the grinding machine. The total power required will be much higher for the grinding machine than for the milling machine. If you
Okay,
are
sir.
if you are using different workpieces, different cutting conditions and different depths, then we cannot compare, right? We can compare only if the conditions are same, then only we can compare one particular parameter. So that is what I'm saying.
Okay, sir.
Yeah. So should we move to the next problem?
Yes, sir.
Yeah. Okay. So the next problem is so the plowing refers to which of these? Material removal only, material removal, displacement sideways only, rubbing against the material only, or all of the above?
Material removal.
Okay. Any other answers? So basically, plowing is the use of blunt abrasives when the abrasives are blunt or not aligned properly, like an abrasive like this. Okay, so this is either a blunt abrasive or the abrasive is inclined at an angle such that it is not able to properly penetrate into the workpiece. In this condition, what will happen is that the force will not be significant enough to cut the material or remove the material, but it will only displace the material sideways, like a blunt hammer. Like you can imagine a blunt hammer, a hammer and a knife. If you put a knife then there is a chance that the material will remove. But if you put a hammer, it will displace the material sideways. Okay, so plowing refers to displacement of material sideways, but no material removal. Okay, so
We can actually compare this with the plowing in the field, like it will be moving sideways.
it will move. Sorry.
We can compare this with that plowing in the field, like the soil will be moving sideways only, it won't be
But
removed.
if you plow in the field, then there essentially you are removing some mud when you plow. But here there is no material removal. There might essentially be a the sideways displacement when you plow a field, but there is also a significant material removal. You are able to remove the material from that. So that is not essentially the how you can compare it. But you can compare it if this is a workpiece and you are trying to strike this region with a knife, then a sharp edge of the knife will tend to remove the material. But if you are striking this with a hammer, then it will not remove the material, but it will just displace the material sideways and make an indentation, something like this. So that is what is plowing.
Okay.
Yeah. So okay, so I guess today we will stop for today, and we will continue our discussion related to grinding and continue the questions related to grinding in the next class. Okay, so I hope,
So,
yeah,
sir, actually, in the previous classes, is it the metal cutting covered? I mean, actually, I was joined this class. So, have you covered any metal cutting like tool life equations on
yes,
the previous class?
yes.
Okay, sir.
We have discussed the tool life equation in the previous class, and some relations of the tool life with the cutting speed and the temperature has also been discussed. So I advise you that you can the link will be shared very soon, like from the NPTEL team to the students in the website itself. So you can go through the study material, and if you have any doubt, you can ask.
Okay, sir. Sir, can you share your mail ID? Or,
See, I can share, but this is I am not uh, supposed to interact personally with the NPTEL students. Like it has to be if you have any interaction uh, or you want to clear the doubt regarding something specifically related to the theory classes, then you can contact the TA of the uh, host institute. Otherwise, like whatever related to the live session problems, you can uh, ask me in the class. But like it has been forbidden for us to you know get in
okay, sir.
any personally in touch with any particular student. So if there is any doubt, you can still ask like in the live sessions itself.
Okay, sir.
And for the doubts related to the theory classes, I would advise you to make use of the discussion forum in the website of NPTEL of this course. So because the professor as well as the TAs of the host institute are directly connected to the discussion forum of that website. So they will be able to give you a proper answer or how to
Okay, sir.
approach a question. Yeah. Okay. Yeah.
So one more thing is, sir, how you are getting this previous year assignment questions? Like, is there any way for the NPTEL team to get previously the we can actually direct download it from the site when we search any course.
Yeah.
So, but now the courses are actually archived. They are saying like if you try to download the previous assignments of any particular course.
Actually, there is this issue that the previous year questions are not being made available to the present students directly. But whatever I am solving in this, like in the live sessions, will consist will essentially consist of all the previous year questions. Okay, in addition with some other problems. We as teaching assistants are being made available those questions, but it is not being made available to the students. Yeah. So
Okay. So
it
if
is not.
we
There is
made
no
an
such way. Yeah. I
so
mean,
if we mail to the particular course, then is there any possibility we will be getting that previous assignment? I mean, the assignments of the 2018-19 course, like which now, like the theory of machinery, something we are not actually getting that course now. So,
yeah, I
is
think so that if you mail the instructor specifically, it is up to his choice if he wants those to be made available to you or not. So you can try and mail them. So it is up to their choice, I think so.
okay, sir.
Yeah. Okay. Okay. Then see you in the next class. Next Tuesday from 6 to 8. Yeah.
Thank you, sir.
Yeah.